Yeah, dear speakers, colleagues, and delegates, we have Dr. Amit Verma with us for his talk on wide-bandgap semiconductors based high-power electronic devices. And I'm very happy to introduce Dr. Amit Verma. Dr. Amit Verma is currently an associate professor in the Department of Electrical Engineering and Professor T.R. Vishwanathan Young Faculty Fellow at IIT Kanpur. He also holds an adjunct faculty position in the Material Science program at IIT Kanpur. His research interests include thin film growth, fabrication, and the characterization of devices based on wide bandgap semiconductors and phase change materials. Before joining IIT Kanpur, he obtained integrated MTech in engineering physics from IIT BHU, Varanasi in 2010 and a PhD in electrical engineering from University of Notre Dame, USA in 2015. Subsequently, he worked on oxide growth and devices as a postdoctoral fellow at Cornell University, USA. And I'm very happy to invite Dr. Amit Verma for his session. So please, sir.
So good afternoon, everyone. So this workshop is more focused on packaging and reliability along those lines. But what I will be talking about is wide bandgap semiconductors, big high power electronic devices. So even though this is not exactly packaging, but for wide bandgap semiconductors, the packaging is actually a very important aspect. Because these are high power devices, that heat has to be taken out of the device very efficiently. So the packaging becomes quite important. Also, very new kind of packages are being developed, say for GaN HAMs or other wide bandgap devices, because they switch at high speeds. So there should be less parasitics coming out of the packages. So in that sense, it's relevant and somewhat related to the theme of the workshop. So let me start by giving a brief overview of what are the different high power applications when we are talking about it. So if you look at this figure, so essentially, so logic, of course, works at only a few volts. Now, the high power applications are some which we are very familiar, we are using day to day. So there are applications which are relatively low voltage, less than 200 volts, such as laptop chargers, mobile chargers, our power supplies, computer, different kind of power supplies that are there, audio amplifiers. Then there are some medium voltage applications, which are very popular, becoming like electric vehicles or hybrid electric vehicles. As more and more renewables are getting installed, ultimately they generate DC voltages, which has to be uploaded to the grid. So it has to be converted. So there are inverters which work around 600 or 900 volts. And this is becoming increasingly important as we are aware, as we go, we kind of integrate more and more renewables into our grid. And again, driver motors, UPSs, so essentially for self-electric vehicles. And then there are very high voltage applications, multi-kilovolt applications related to wind turbines, driving of ships, metros, and electric trains, and then even higher for power grids, so high voltage DC transmission. So you can see these are very high voltages, but this is not the only requirement. Along with the high voltage, we have to look at the current requirements for these applications also. So in this figure, you can see for some of these applications, so x-axis is the voltage rating in log scale and y-axis is current rating in log scale. So you can see some of these. So for example, different kind of power supplies might need up to about tens of amps of current. You go to the electric vehicles, it might need 600 volts to 1000 volts, but current ratings are about 100 amps. And it keeps on increasing as we go to metro trains or high voltage DC transmission. So the devices that we use in these systems should be able to handle voltages in these range and currents in these range. Okay. There is another aspect to it. So some of these applications, so there is current times voltage is power, essentially, which we want to supply to that load. Now, some of these loads have to be switched at relatively high frequency. Only then they operate properly. So x-axis, you can see there's the system operating frequency. So essentially, the switches which we have to use for these applications should be able to switch at relatively higher frequencies. So the question is now again, what are the devices? Why wide bandgap have a role to play in this? Why would they do these switchings better than silicon? So let me motivate that by going through the basic physics of how these things operate. Okay. So let's take a typical high power application. So you can see here, I have a load. This can be anything. It can be a motor in an electric vehicle, for example. I have some supply. This need not be DC. It can be DC or AC source. And essentially, I want to control the flow of power from this source to this load. And I should be able to switch on and off using some switch. And these are usually semiconductor switches. So you can see in the off state, so this voltage would be some large voltage I already showed you. And there would be some current rating which this load would need. So when the switch is off, essentially all the voltage drops across the switch. So the semiconductor switch should be able to sustain and not break down under that voltage. Also, so this is one of the important aspects of the power switch. The other is in the off state, there can still be a small leakage current through this. We want this leakage current to be as low as possible because the voltage drop is large. So if the leakage current is significant, the product or the power dissipation in the switch can be large, which we do not want. Now we look at the other state of the switch, which is the on state. So in this case, essentially we want all the voltage to appear across the load and a very large current to be flowing through it so that all the power is delivered to it. Now in this case, ideally, of course, the switch should have a short, but we know that there are no ideal switches. So this switch actually can have a small resistance or a small voltage drop across it. So I'll give examples later. So because of that, actually because large current is flowing through it, there is significant power dissipation that can happen in the switch itself. Also, we want the switch to be able to sustain high currents. So I showed you some applications need 100 or even 1000 amps of current. So this switch should be able to handle that. So these are two more parameters in the on-state. So on-state resistance or forward voltage drop of the switch or on-state current capability of the switch. In addition to this, as some loads want to be switched between on and off states at a certain frequency, when we switch, we should be able to switch rather fast. I'll tell why. Okay, so now let's look at the switching waveform of such a circuit. Okay, so if I have an ideal switch, essentially in the on state, these are what we are plotting is the current through the switch and the voltage across the switch. So the current is rather high in the on state and the voltage ideally should be zero, drop across the switch so that the product of voltage times currents is zero and there is no power dissipation in the switch. Similarly, in the off state, we would want all the voltage to be dropping across the switch and no off-state leakage current so that again their product is zero and we have no power dissipation in the switch. And we would want this switching to happen instantaneously so that even during the transition, the voltage times current product remains relatively zero or the integration under VI curve remains zero. So there is no power dissipation in the switch. All power gets delivered from my AC or DC source to the load. This is an ideal switch, of course. In reality, of course, nothing is ideal. A real switch might look something like this. So in this case, in the on state, you have a forward current, but then the voltage drop across the switch may not be zero. It might be small, but it will be non-zero. So the product of IF times VF gives us a non-zero loss in the on state of the device. Similarly, in the off state, there is a leakage current, which is non-zero. So their product again can be significant. So usually in good switches that are in use, usually leakage currents are not that important. So off-state static loss is usually not that important. Now, the third aspect is this transition from on-state to off-state is not instantaneous. It takes finite amount of time. And similarly, the voltage rise takes finite amount of time. So if we look instantaneously at each point, there is an instantaneous power dissipation. And if you integrate over it, there is a finite power dissipation that happens during the transition. So this is the dynamic power dissipation essentially. So if we switch multiple times more and more at a higher frequency, this power switching will scale with frequency. So it will keep on going up. Okay. So essentially these three power losses reduces the efficiency. We are not able to transfer the power 100% from the source to the load. And this is just lost as heat in the switch, which ultimately we have to cool and take out. So there are essentially two kinds of power devices that are used to do these things. One are two-terminal devices. These are essentially like diodes, power rectifiers, which control the current. So if there are loads which allow, through which you want the current to flow only in one direction, one can put these devices in series with these loads. So an ideal rectifier characteristics would look like this, essentially looking like a diode characteristics, but this is the ideal one. So in the reverse, there is no off-state leakage and it can sustain very high breakdown voltages. In the on-state, it can allow any current to pass through it with no VF, no drop across the device. Okay, this is ideal. How does a real diode look? It will look something like this. There will be a cut-in voltage, and then there would be a finite resistance of the diode. So if you try to pass more and more current, the voltage drop across this increases. Also, if you look at the reverse bias, the leakage might not be negligible. It can increase with the reverse bias, as well as it will break down at some voltage. In addition to this, because this is a PN junction, if you go from forward bias to reverse bias, one has to remove the minority carriers. So there can be reverse recovery related effects also, which one has to consider. So another power device that is often used is a switch. So this is a three-terminal device like a transistor. This essentially controls how long the current flows through the load. So we control this, use some controlling circuitry through the gate terminal to control how long the current will flow through the load. Again, an ideal switch will look, its characteristics will look like this. In the off state, it will not allow any current to pass. You can drop very large voltages across it. In the on state, it can allow any current to pass with no voltage drop across the device. How does a real switch look? Something like this. So there is some finite leakage. It breaks down at some voltage. In the on state, there is a linear region. So if you want to pass certain amount of current, there will be a finite voltage drop across the device. So there will be a on state power dissipation across it. So how do we quantify the efficiency of switching essentially in this process? So this is a very short back of the envelope kind of a calculation in Mathematica. So what I assumed is these numbers, these are very typical numbers for some application, but of course they will change from application to application just to show you how things scale. So let's say I have a switch whose on resistance is 0.1 ohms, forward voltage drop of 1 volt. Forward current is 10 amps. The reverse voltage is about 100. So this is the load is about 1 kilowatt load. And let's say the leakage current is about 0.1 milliamps. So significantly low. And I'm switching on and off this switch at 50% duty cycle. So it is on for 50% of the time and 50% time it's off. And the transition time from on to off or off to on is 1 microseconds. So it's not zero, it is some finite amount of time. Okay. So if I plot the losses now, in as a function of switching frequency. So you can see, so the static loss, because for half of the time the switch is off, no matter what the switching frequency, the static power loss is constant and it's relatively low. The on-state static loss is again independent of frequency and at some level, but much higher. And then there is this third loss, which is the dynamic loss, which scales at frequency because now there are more transitions from on to on and off to on. So every transition causes loss. So this scales with frequency. So this is a very typical loss curve of any switch. Of course, as these values will change, the curves will move around and the values will move around. So you can see for applications where the switching needed is at very low frequencies, what matters is the on-state loss. So we would like that to be as low as possible. For applications where switching is needed at relatively high frequency, the dynamic power loss actually dominates the total power loss. So if we look at the efficiency of power transfer from the source to the load, so at low frequencies, the efficiencies are rather high, right? This is very typical. You can get 98, 99% efficiencies. But as you go to higher switching frequencies, this efficiency really drops. So any device which can help us, so for applications which require high frequency switching, any device that can help us to reduce the dynamic power dissipation by essentially making a fast transition can really help in saving or improving efficiency at these frequencies. And you might think that these efficiency numbers are these are already very high numbers. So you might think, what can be an impact of increasing an efficiency from 95 to 99%? It's a mere 4%. But you have to think that probably in our houses, we have 10 appliances which are high power, and they use probably, I don't know, 100 or let's say even 10 devices like this, right? And we are about, right, world over, population is 7 billion. If you multiply that, and that 4% actually turns to be a huge number. So actually, it will save many new coal power plants to be built if we can actually make these small changes in improvement. So that's what power electronics is all about. Okay. So now let me come to the question of why wide bandgap should be useful in this purpose, right? So in early 80s, Professor Jayant Baliga, he came up with this figure of merit for unipolar devices. It's a very simple figure of merit that makes the point. So let's say I have a rectifying Schottky diode. This is a vertical device, very typical device which gets used. So essentially there is an anode, there is a very low doped drift region. This is typically tens of microns thick on a highly doped substrate, and then you have a cathode terminal. So it's just a diode essentially. So this region in the forward bias, there is no depletion region. So essentially this whole region acts like a resistance, that is the on-state resistance of this device. In the reverse bias, we deplete the drift region. So there is a big depletion region here with the field profile looking something like this. Because the doping is uniform, the field profile linearly varies with the field peaking at the anode and drift region interface. Okay. So we can do a quick calculation. So in the on-state, essentially there is no depletion. So this is what contributes to on-state resistance. So this is what's called as a specific on resistance. It's proportional to WD, this width of the drift region, because the current flows in this direction. So essentially this is the length of the resistor, and it is inversely proportional to the doping in this region because the doping reduces the resistance. Then if we say that when this gets completely depleted, that is my breakdown voltage. So the field, maximum field at this interface is the breakdown field, critical breakdown field of that particular semiconductor, wherever we have made this device. So the area under this curve, essentially half of WD times EC, is the breakdown voltage. This is this equation. Okay. We also know how to relate the depletion widths with doping. This is standard diode physics. It's something like this. So we can play with these equations and derive this equation, which relates the specific on resistance with the breakdown voltage. You can see there are semiconductor parameters at the bottom. This is dielectric constant, which is similar for most materials, does not change by much. Mobility again can change maybe by an order, not beyond that. This is the critical breakdown field. It goes as the third power cube, and it's very important in deciding this trade-off. So why there is a trade-off? So you can think, see, I want to reduce Ron. So what I can do is I can make this region thinner. I can reduce WD. But then if WD is less, I cannot drop a lot of voltage across it. So my breakdown voltage also decreases. So there is a trade-off. So this parameter, this product is called as Balliga figures of merit, and this is what we use to compare semiconductors. Now, as I told you, epsilon s and mu n do not change very significantly between semiconductors, but EC actually scales as a square of the band gap. Okay. So in this figure, y-axis is the critical breakdown field, x-axis is the band gap of a semiconductor. So silicon is somewhere here about 1.1, so a little higher actually than that. It's very difficult to get significant breakdown in it. As you increase, right, you keep on increasing to gallium nitride. This is one of very popular materials. Band gap is about 3.4 eV. Breakdown fields are about 4 megavolt per centimeter or so. You go to even larger band gaps. I'll talk about gallium oxide a bit, which is about 4.8 eV. The breakdowns are about 7 to 8 megavolts per centimeter. And because these numbers are going as cube here, this has an incredible impact on this trade-off. Okay. So how does the trade-off work out then? So what this curve shows is essentially plotting this Balliga's figure of merit. The y-axis is on resistance, x-axis is the breakdown voltage for different typical semiconductors. Silicon, of course, is used, but then many of the wide bandgap and ultra wide bandgap semiconductors. So you can see for a particular application, let's say I want to make a 100-volt switch. Compared to silicon, gallium arsenide, I can make that switch with a much lower on resistance because I can dope it heavily. If I do the same with silicon carbide or gallium nitride, I can get even lower on resistance. So as on resistance goes down, I can reduce my power dissipation. So essentially the switching efficiency goes up. That is what I was mentioning, small improvements in switching efficiencies. Okay. So if you want to develop any of these technologies, okay, what are the critical sub-technologies? Some of the technologies are low doped, high quality drift layers. So the drift layer, top layer I was showing. So growing very high quality layers with very low defects and low doping. Low doping, I mean, is about 10 power 15 per centimeter cube, 10 power 16 per centimeter cube or so. So that they show large breakdown and high mobility. Then we also need high doped layers. So like the bottom one to make good low resistance ohmic contacts so that on resistance remains low. Then we also need low leakage Schottky contacts, that the top contact. So because these devices have to carry large currents, typically their areas are large, many times even covering full wafers for a single device. So we want very low defects in these films so that there is low leakage through the Schottky contact, or there are some MOS structures also. So we want low leakage in them. Now to reach these limits of the critical field, lot of field management has to be done. Field plates, resurf. So there are different techniques by which we manage the field so that we can reach these effects. Because once we have finite size devices, there are edge effects that play a part where corners, the electric fields are highest. So usually breakdowns happen there. So we do field plates to manage and reduce those fields. Then we have to develop both lateral as well as vertical devices because, again, they have their own advantages, disadvantages. Beyond that, because ultimately they are handling large power, even if their efficiency is very high, that small inefficiency of few percent can lead to very high numbers in heat generation. So that heat has to be removed from the chip. So usually it has to be packaged very well. Also, as I mentioned, these devices sometimes have to switch at high frequencies. So the parasitics which the package adds, any inductance or capacitance, has to be minimized also. Otherwise, it slows down the switching from on to off or off to on states. So package actually is a very important part of high power devices. So beyond this, let me focus and show about beta gallium oxide, because this is one material we have been involved with. This material has a band gap of about 4.8 electron volt, and we have been involved in it for some time to kind of develop some of these sub-technologies. So you might ask that among silicon carbide GaN, right, why we should work on gallium oxide, and there are a couple of reasons for it. So this is a comparison table of the different materials. So one is, of course, obvious that the band gap is very large. So you can see that the breakdown field is much larger than silicon, gallium arsenide, silicon carbide, and GaN. Because of that, if you look at Baliga's figure of merit, it's much higher, which leads to efficient switching. If you look at high frequency figure of merits, there are several other figure of merits. There also, it's quite good. There is one kind of limitation or challenge of this material is thermal conductivity is not as good. So heat removal, one has to do a lot of device design for that part. Okay, so there's a lot of work going on along that direction. So essentially, it has very high figure of merit for power switching devices, but there are still research needs to be done for good heat extraction strategies, package design, etc. Okay. And this is a relatively new material. I was doing still my PhD. At that time, the first gallium oxide devices with 100-volt breakdown came out. These are Schottky diodes. And then the next year, essentially MOSFETs, first MOSFETs were demonstrated with breakdown of close to 370 volts or so. So just 10, 12 years, people have developed now devices with multi-kilovolt and tens of amps of these devices. So this has developed really quickly. Other than that, there is a very big advantage of gallium oxide relative to silicon carbide and gallium nitride. That is the availability of bulk substrates. Typically, you will make a power device on a substrate. So that substrate cost should be low enough, and it should be available in large area. Now, silicon carbide and GaN actually cannot be grown from melt like Czochralski. So silicon, we know, we usually do Czochralski, but in silicon carbide and GaN, you cannot do that. Okay? So they are usually grown by vapor phase methods. On the other hand, gallium oxide can be grown by melt growth. So that is one big advantage, which has allowed. So this is a rather dated photo from 2022. So there is a dedicated workshop for gallium oxide. It's called International Workshop on Gallium Oxide. So this is a photo from there, which we were attending. So essentially, these are the latest. So this is 6-inch gallium oxide bulk wafers, which are already in development, 4-inch wafers, which are commercially available. These are big Schottky diodes fabricated on the full wafer, and these are diced and packaged kind of devices. So all of this scaling, device development, all of this has happened in last 10, 12 years or so. So very fast development, and it's a big community that is now contributing to this. Okay, now let me just summarize about what work we have been doing here at IIT Kanpur. So essentially, we are going all the way from growth. So we have set up a multi-zone, it's called as a low pressure chemical vapor deposition system, in which using gallium and high purity oxygen and argon as precursors, we can grow high quality epitaxial beta gallium oxide films on both either sapphire substrates, GaN substrates, or on bulk gallium oxide substrates. More recently, we have demonstrated controlled doping of these films using a liquid precursor called tetraethyl orthosilicate. So silicon is the N-type dopant in this material. And by controlling the flow rate, we could control the sheet resistance by almost 6 orders of magnitude. The as-grown films are usually highly insulating. But in this, by putting in the dopants, we are able to control the resistance repeatably. When we do Hall measurements, this converts to controlling carrier densities from 10 power 17 to about mid 10 power 19 per centimeter cube or so. Okay. Another thing, this is very interesting, is usually for dry etching of any material, we have to use reactive ion etching kind of chambers where we use either chlorine chemistry or fluorine chemistry. With gallium oxide, actually a very interesting thing is if you put gallium flux on gallium oxide, it can reduce it to Ga2O, gallium suboxide, which is volatile. So using this method, just using the growth system and cutting off the oxygen supply, we patterned it, of course, with SiO2 mask. We demonstrated etching of these films. So essentially using the same system, we can do growth as well as etching by just controlling the precursor flows. So that makes actually this a very powerful system because you can do in situ etching as well as growth in the same system. Okay. Now with these, then we have developed Schottky diodes. So these are vertical diodes. These are very initial devices that show related 20 to 40 volt kind of breakdown, and we are working to improve them further. Another application of these materials is because their band gap is very large, when visible light falls on them, they do not generate electron hole pairs. But if a deep ultraviolet light, so the band gap is 4.8 eV, that corresponds to a photon of 260 nanometer. So if your photon energy is less than 260 nanometer, it can generate electron hole pairs and change the resistance of the material. So one can make deep ultraviolet solar blind photodetectors using them. These have applications, a lot of in water purification, missile detection, a lot of different applications. So again, using the gallium oxide we have grown, we have been able to get good photo response out of this. Okay. So with this, I'll just end my talk. So essentially, let me just thank the organizers, of course. Some of the work, gallium oxide I shown was supported by SERB, which is ANRF now, by an early career research grant. And yeah, this is my group at IIT Kanpur, and these are the people who contribute to the gallium oxide work. Okay. So thank you for your attention.
So delegates may post their questions in the YouTube chat box so that I will raise it to Dr. Amit Verma, sir. Just I will collect the questions.
Okay, in the meantime, we have questions from audience. So let me ask a question. So what is any specific thing in terms of package for the sigmas for the GaN FET? As you mentioned that even the bonding wire is going to cause some stray inductance, which is going to affect the maximum switching frequency. So what type of bonding, what material is used for the bonding wire, or any special, consideration that has to be taken care for packaging the SiC or the GaN FET devices?
So I'm not a packaging expert, so I know that is important, but yeah, I can't answer that.
Okay, that's fine. Right.
Yes.
Right. Okay.
And there is a request from the
Sorry, I can't hear you.
Yeah, can you explain again? Some of the student participants have raised question. They are asking you to repeat the topic of efficiency. Just can you explain again?
Sure.
Switching losses and conduction losses. Yeah.
Yes, sure. So see, essentially, so let me go back to that circuit. Yeah. So essentially, I have a power source and I want to transfer that power to the load. I want to use the switch only to switch the power. Ideally, there should be no loss in it. But again, because the switches are not ideal, some of this power gets dissipated here and rest is supplied to the load. So the efficiency is what power gets supplied here divided by the total power. Okay. Now there are three sources of loss in the switch. So the three sources are loss in the on state because there is a large current going through the switch, and there is some small voltage drop across it. This can be, let's say if you are a diode, this can be the cut-in voltage of the diode. So there is a drop. So this is some small voltage times this large current gives you some static power loss. Then in the off state, you have a very large voltage drop across the switch and a very small leakage current going through it. So again, their product gives you a static loss. Then when we are switching from high current to low current and low voltage to high voltage, the switching is not instantaneous. It takes some finite amount of time. So during this time, at each point, there is some large current flowing and there is a finite voltage drop. So their product gives an instantaneous power, which we integrate over this transition time, gives us some power loss during the transition. So off to on and on to off. So this is the dynamic power dissipation, which will scale with frequency, because as you increase frequency, there are more of off to on and on to off transitions. So when I was showing, so essentially, so let me go back to that calculation, right? So these are some typical numbers I took, and these are the losses now, right? So you can see here, there is a static loss in the off state, rather low. We did not worry about it. On state, there is a loss because the current is about 10 amps. The drop across the forward voltage drop is 1 volt. So that is 10 watts. But then the duty cycle is 0.5. So the switch is on only for half the time. So that's why that loss is 5 watts, which you see over here. Then there is the dynamic loss. This is the red line, which scales with frequency. So more transitions, more loss. And you can see the transition times are about a microsecond. So as I approach a frequency of a megahertz, which has a time period of about a microsecond, you can see this loss is almost equal to the total power we are supplying. So essentially no efficiency. So all of this loss essentially reduces our efficiency because this is not supplied to the load. This is just converted into heat in the switch. So that is this curve. So at very low frequencies, the loss is fixed about 5 watt. So rest is supplied to the load. So it's very high frequency. As you increase frequency, this dynamic power loss also picks up. So the total loss is higher. So efficiency drops. So I hope I explained that. Yeah. So if there's any follow-up, let me know.
Yeah, there is. Yeah, one more question, sir.
Mm-hmm.
Like you have mentioned about the poor thermal conductivity of gallium oxide.
Yes.
So what are all the considerations to be done in the device level?
Right. So some of the things what people are looking at is, of
Sir,
course,
have you got my?
I got your question. Yes.
I think please 1 second.
Yes.
Sir, Amit, sir.
Yes, I can hear you.
Yeah. So you have mentioned about the poor thermal conductivity about the gallium oxide.
Mm-hmm.
So what are all the considerations to be done in the device level using gallium oxide? This is a question from one of the participants.
Okay. So some of the things that are being pursued are, of course, integrating. So of course, before packaging, to reduce the thickness of the substrate, because the device is only in the top few microns, tens of microns. So reduce the substrate thickness so that the heat can be removed efficiently from the bottom. And then integrating these thinner ones on low cost, high thermal conductivity, let's say polysilicon carbide substrates. So there is a lot of work going on integrating gallium oxide on these low cost, high thermal conductivity bases. Other than this, people are also working on actively involving other high thermal conductivity materials in the device itself. For example, there is work going on nitride and oxide integration because nitrides have relatively higher thermal conductivity. So that is another approach. So they are part of the device now, and they help in removing heat from the top itself. So this is another approach. From the top also, people are working on integrating CVD nano diamond on top to remove heat from the top side now in a flip chip kind of a configuration. So several of these approaches are being tried out. It's a very active research area right now. Actually, work on packages has just started to kind of happen over last couple of years only.
Yes, sir. So another question, like a diamond seems to have better band gap than gallium oxide.
Yes.
So are
Yes.
there any, devices coming up using diamond?
Yes, there are devices coming, but the issue is again having low cost substrates. So, diamond is very high cost. So having large area diamond substrates of low cost does not seem very feasible. So that is one challenge for sure. But devices are certainly coming out. There are groups working on it.
Great. Question. Yeah. So thank you so much, sir. Amit sir, having accepted our invitation to deliver a talk in this workshop, and we thank you very much for your time and the presentation.
Yeah.
So
Thank you very much. Thank you very much for the invitation.
also, we take this opportunity to invite you to Sastra.
Sure, sure.
Sometimes, when you come down south, please visit us. And there is a group working on devices, especially on HIMT.
Okay.
Yeah, there is a device modeling group. They have been extensively using the TCAD stuff, synapses, etc. So that we would be happy to have you here in our campus.
Sure, sure. I'll certainly try. Yeah. Yeah. Okay. Thank you.
Thank you so much.